video deals with the topic of Introduction to Filters. This video is very important in order to understand the few basic points or to gather the basic knowledge regarding filters, which will be useful when we study designing of digital filters. Now this is the characteristics of an ideal low-pass filter. Here we have plotted the magnitude of Fourier transform of the impulse response of a low-pass filter system with respect to its omega. And we know in the topic of DTFT, the range or the band of vision that we are concentrated to is from minus pi to pi. So we have shown till minus pi to pi. Now for an ideal low pass filter, the value or the magnitude of the filter would be 1 till omega c, which is the pass band, that is from 0 to omega c, and from omega c to pi the magnitude would be 0. Now we have shown both the positive and the negative frequencies. As we know, for every positive frequency there should be a negative frequency theoretically, but in reality or in practicality negative frequencies do not exist. Now, in order to find out the impulse response of such a system or impulse response of this low pass filter, we can find out Hn by the inverse DTFT formula, which is given here. But we know from omega c to pi in both the directions the magnitude h of ej omega is 0. So we should be concentrated not from minus pi to pi but from omega c to minus omega c to plus omega c, where the magnitude of h ej omega is 1. So if we perform the inverse DTFT, we find out the value of Hn would be sine n omega c by n pi, which is not equal to 0 for n less than 0. That means the magnitude of Hn is not equal to 0 for n less than 0. That means it is a non-causal signal. And as mentioned in the topic of signals and systems, we all know that a non-causal signal is not a practical system. Non-causal system is not a practical system. It can exist theoretically only. And in fact, it is not even a stable system because the summation of Hn is not less than infinity. That is, it is an unstable system. So from now onwards, we know that an ideal low pass filter is good to visualize theoretically, but practically is not a stable or causal system or not a practical system. So in order to have a more practical low pass filter, the graph or the plot should be a monotonically decreasing plot rather than a drastical or a sharp plot that the ideal characteristics shows. We know nature abhors anything which is very drastic in nature. So here also the graph should not fall to 0 drastically, rather the fall should be gradual as shown by the red line. Here we again need to define omega c, that is the cutoff frequency. Now the cutoff frequency is the frequency where the magnitude of the low pass filter should not fall below alpha. That is, mod of h should lie between alpha and 1 for the range of frequency 0 to omega c. Now alpha is usually 1 by root 2, that is, if we take 20 log 10 of 1 by root 2, it is minus 3 dB, because 20 log 10 of 1 is 0. Anything below that is in negative. So it is the minus 3 dB point, or when the magnitude falls 3 decibel lower than the maximum magnitude, the frequency is called the cutoff frequency. Now, the 0 to omega c band is called the pass band. We have to here define another point, that is the beta point, and the magnitude is beta, and the corresponding frequency where the magnitude falls at beta is the stop frequency, that is omega s. Now omega s to pi is the stop band, and in between this pass band and stop band lies the transition region. That is, the characteristics of a required or a practical low pass filter should not go from pass band to stop band. It should have a transition region in between, and more the sharp the transition region is, more better filtering it does. Now some simple digital filters equations. These are all finite impulse response filters. Filters basically are of two types, IIR filters and FIR filters. IIR means, as the name suggests, are infinite impulse response. The impulse response of such filters will be infinite, and for FIR filters the impulse response would be finite. Now here digital filters would be written in terms of in z plane. Now hz is equal to half of 1 plus z inverse. Now we know z is equal to e to the power j omega. Now we replace z by e to the power j omega. Now we are concerned about 2 points, that is omega is equal to 0 and omega is equal to pi. When omega is equal to 0, we see that the magnitude h e j omega is 1, and when omega is equal to pi, the magnitude becomes 0. That means it is a low pass filter. That is, it stays from 0 till pi, it stays at 1, and when the frequency is pi, it becomes 0. That is, it is a simple digital low pass filter. But from now onwards, we do not need to change z into omega. From now onwards, we know when omega is equal to 0, if z is equal to e to the power j omega, when omega is equal to 0, then z is equal to 1. And when omega is equal to pi, z is equal to minus 1. So whenever we have a digital filter, just in order to know the magnitude at 0 and pi, which are our concerned points, we just need, for omega is equal to 0, we need to put z is equal to 1, and for omega is equal to pi, we need to put z is equal to minus 1 and see the magnitude of hz, and from there only we know whether the filter is low pass or high pass or band pass or band stop filter. Now hz is equal to half of 1 plus z inverse. If we replace it by e to the power j omega, and we can write this as e to the power minus j omega by 2 cos of omega by 2. I have ignored the subsequent steps. Now here the magnitude of h e j omega would be magnitude of cos omega by 2. So when omega is equal to 0, we know cos 0 is 1, and when omega is equal to pi, cos pi by 2 is 0. So here it is a low pass filter, but not at all a good one. Now if we are interested in finding the cutoff frequency, then we know by the definition of cutoff frequency, the magnitude of the low pass filter becomes 1 by root 2 when omega is equal to omega c. So here we can write the magnitude is 1 by root 2 when cos omega is replaced by omega c by 2. So from here we know omega c is equal to pi by 2. So the cutoff frequency is pi by 2. Now, as discussed before, the ideal, or I should say the practical or more desired characteristics would be the blue line. Now, in order to get that desired blue line, so anything, it is, see, the highest point here is 1, the blue straight line. Anything beyond or lower one, say 0.9, if you square it, it would be 0.8, it lowers. So what we can do in order to get the desired or the lower or more monotonically decreasing characteristics, we need to square or keep on multiplying the low pass filter. That means we can cascade more low pass filters together in order to get the ideal character, or should not be saying ideal, or more desired characteristics, but cascading means increase in cost. Now hz is equal to half 1 minus z to the power minus 1. This is an example of a high pass filter, because z is equal to 1 yields 0. Z is equal to 1 means omega is equal to 0, and z is equal to minus 1 means hz is equal to 1. So at omega is equal to 0, this is 0, and omega is equal to pi, it is 1. So it is a high pass filter. And h e j omega we can write as j e to the power minus j omega by 2 sine omega by 2. So here also the magnitude would be 1 when omega is equal to pi, because sine pi by 2 is 1, and magnitude is 0 when omega is equal to 0, and omega c again is pi by 2. From here we can see, if we compare the two high pass and low pass simplest digital filters that we have studied here, if we replace z by minus z by minus z into a low pass filter, what we get is a high pass filter. If we have an expression of low pass filter, in that expression if we replace z by minus z, what we will get is a high pass filter. The logic is again very simple. Z we know is e to the power j omega. So minus z would be e to the power j omega plus minus pi. Let us say minus pi. So what was happening at omega is equal to 0 will now happen at omega is equal to pi. This is what is a low pass and high pass filter. Difference between low pass and high pass filter. Now this is a band pass filter. We are passing the frequency between 0 to pi. So say we have hz is equal to a into 1 minus z to the power minus 2. Now this can be written as h e to the power j omega twice a j e to the power minus j omega sine omega. So its magnitude would be sine omega. So at omega is equal to 0 we have 0. Again at omega is equal to pi we have 0. But we should have a maximum at some point. Sine omega is maximum, that is equal to 1 at pi by 2. So the maximum point is pi by 2. And if a is equal to half, we get magnitude 1. So hz is equal to half 1 minus z to the power minus 2 is a simplest digital band pass filter. Similarly, hz is equal to half 1 plus z to the power minus 2 would be a simple digital band stop filter, also called notch filter. So this is all about the simplest introduction or the integrities of a filter. So here we will stop today and we will proceed with some more topics about filters.